Welcome everybody to our next presentation. It's now that time, so I am happy to introduce Joseph Eichholz from United States Air Force Academy with his presentation using differential algebraic equations to model classical mechanics.
All right, awesome. Can you guys hear me? Kurt, can you hear me? The answer is yes. Okay, cool. Well, thanks, Anna, Kurt, Sandra, for coming to this talk. I want to talk a little bit about introducing differential algebraic equations in an undergraduate ODE course. We'll really do, kind of a standard talk. We'll talk about history, motivation, goals, and then kind of the framework, and then some software we've developed, and then the classroom experience. And really, this whole thing started, as with all of my best ideas, by watching YouTube. And I was watching YouTube, and I'm not sure this is going to work. Am I sharing the screen itself? Can you guys see YouTube now? Yes, awesome, right? So, I was watching these videos with the synchronizing metronomes, and those are pretty awesome. And then you can watch other ones, the coupled pendulums. This isn't a very good video, but I really like the coupled pendulums, and your pendulars are exchanging energy back and forth. And I really like this one, right? You've got the objects rolling along a rotating disk, and you wonder, is that thing ever going to fall off, or what's it going to do? And if you watch for long enough, it seems to travel along a closed orbit, and that's kind of amazing to me. And it turns out, yeah, those do travel along closed orbits, which is amazing. And so I was doing this, and I was thinking, wouldn't this be cool if we could model it in an undergraduate, like in a systems of ODEs class? If we could do that, then, well, we'd have all kinds of material for projects and examples and just kind of cool stuff. And it would provide a nice alternative to like compartment models. I don't have anything against compartment models, but so many of the projects I see in an undergraduate systems of ODEs class, they're compartment models. And just to me in particular, I'm more interested by mechanical things. So I kind of wanted to introduce this kind of modeling into an undergraduate ODE course. But the problems with that is we really don't spend a lot of time modeling these kinds of mechanical processes in a typical undergraduate ODE course, right? We do F equals MA, which is most of what you need. But then what do we talk about? We talk about like falling bodies, we do spring mass damper systems, and maybe we do pendulums, and that's probably about it, right? And frequently when we give a derivation or when we actually do the modeling of these problems, we usually give like a really quick, very elegant approach that just gets right to the equations that we want and that the students are never going to be able to reproduce. And so I was sitting eating lunch one day with well, we'll call him a friend. He's an engineer, so I'm not sure you can call him a friend. I was talking to my friend Simon Jones, who's the other author on this kind of stuff. And he teaches a dynamics class in mechanical engineering, and they do talk about these kinds of problems in there. And he was telling me that they had kind of the same problem in engineering, where up until like 15 or 20 years ago, everything was very elegant, and you just kind of had to know the trick to derive the right system of equations for this kind of system. But that in the last 15 or 20 years, they've been moving to a kind of more systematic approach to doing things. And that's kind of what I want. I want a toolbox that we can give our students and we can give ourselves to model these kinds of more complicated systems. And the answer really is that rather than thinking of them as just pure ODEs, we should think of them as differential algebraic equations first, and then maybe convert them to pure differential equations second, if it works out. So the goal, provide a framework with which faculty can develop class examples and projects, and something the students can actually do. So I don't want to go to a Lagrangian approach or Hamiltonian approach or something like that. Like your sophomore students in a DE's class, they're not going to be able to handle that. I want to stick with a Newtonian approach because they can mostly handle that. And then the problem with the Newtonian approach, well, and with Lagrangian also, like stuff gets out of hand pretty quickly from an algebraic point of view. So we ended up writing some software tools to kind of help us out. So I kind of want to take you through what it is we do and how we can get students from nowhere to modeling coupled pendula in basically like 4 days of class time. So 4 days, and then you give them a project, and they can write down equations of motion for coupled pendula, and then they can see the pendula exchanging energy and the whole thing. And it's pretty cool. So some caveats right up front, like there's nothing here new. I didn't invent any new theory of mechanics for sure. We're going to model the motion of one or more objects, possibly connected together. Everything is going to have mass and take up a finite non-zero amount of space. So no point masses, no massless rods, no anything like that. Our objects are going to be non-deformable. We're going to stick to planar motion. And again, the goal here is not to be as general as possible. I could certainly do things more generally, but rather to provide a systematic framework that students can actually get their heads around and actually do some cool stuff with. So day one with our students, I'm going to talk about objects and how to describe the state of an object. And as long as the object is living in the plane and it's non-deformable, all we have to pin down is a position and an orientation for the object. And they really don't have any problem with the idea of what the position of the object is and what the orientation is. We're always going to call the position of the object R. And just because it's easier, the position of the object is always the center of mass of the object. Okay? And we're always going to call the orientation of the object theta. And it's always just an angle of rotation about an axis centered at the center of mass. So it's no problem. I hand them a little worksheet. You know, they spend 10 minutes writing down, okay, for this object, I think the position is this and the orientation is this. They get the idea of position and orientation, and that's enough to describe the configuration, really, of an object in the plane. Once we talk about that, then we're going to talk about the equations of motion. And the good news is there's really only 2 equations of motion, and they already know one of them. They already know F equals ma. We've already done that for, you know, there's 2 differential equations hidden here. But if you're in a systems of differential equations class, it's no problem. They should be able to handle this. The one where they kind of are, you know, struggling to recall, shall we say, is Euler's law that tells us how the orientation of our object changes. And Euler's law says that I theta double dot should be T sub F. And I always have to remind people what the heck do these things mean. The I is the moment of inertia of the object as it rotates about the center of mass. And that's really great because that's the thing we see in Calc 2 and in Calc 3, and then we never do anything with it. It's just kind of a thing we compute and we never do anything. And so it's nice that it shows up here because it's a thing that we will use. And then I can ask them to compute it to set up their models. And T sub F, that's my notation for the torque about the center of the mass induced by force F. So force F is trying to change the orientation of the object, but it does it through torque. And again, this is a thing we see in Calc 3. And again, it's a thing you hardly ever do anything with. And so they frequently have to kind of remember what's going on, that to compute the torque, you should take the lever arm and the cross product with the force, and you should really take a magnitude of that thing. But if you're in 3 dimension, or if you're in the plane, then you just append a 0 at the end of these vectors and you take the third component, and that's going to be the torque that you want. And since we're in the plane, I usually just give them a formula for how to compute the torque of a force induces if it acts on point P, because again, I'm always going to be rotating about my center of mass. So I just give them this formula. And once we have these 2 equations of motion, by the end of class, I'm asking them to write down equations of motion for like a solid rod. So I've got a solid rod of length L and mass M, and I say it's acted on by gravity and a known force. The known force is just this guy that I make up. And I say, what are the equations of motion? And you follow F equals ma, no problem, mass, right? You should have fx, the only thing there is 0.7, and then fy, you should have the negative 0.3, and then you should have the, it's the net force, so you should have the negative mg sitting there. And then this is the part that takes them a little practicing to do, but you've got to express your lever arm in terms of the configuration of your system. So you've got to express it in terms of r and theta. And this is, it's length negative L over 2, and it should be in direction, maybe negative sine theta cos theta. So your lever arm can be expressed that way. You follow the formula for torque. And here you go. Here you have a system of 3 differential equations that perfectly describes the motion of your system. No problem. You've got it. Great. Once they get here, man, you are 90% of the way to being able to describe a pendulum, a double pendulum, coupled pendula, all kinds of mechanical things. Then you've got to calculate your moment of inertia. That's an exercise in Calc 2 because it's all planar. So I just let them do that. And once you're here, you're good to go, right? Okay, so what are we going to do? The only thing that's left is what happens if your object isn't free to move into any configuration. What if it's constrained? What we're going to do is we're just going to describe any constraints to motion using unknown forces. Those constraints to motion, we can express them using algebraic or differential equations. And now we're going to have our equations of motion, and we're going to have our algebraic constraints saying like this part of the object has to stay in this position. That's going to give us a DAE, which is differential algebraic equation. And then if you're lucky, you can convert the DAE back into an ODE using classical techniques. The classical thing is you differentiate your constraints the right number of times, then you solve for your unknown forces in terms of your state variables, and you plug everything in. This is the part that you would have software automate away. The modeling is all in the first 3 parts. The software should take care of the 4th part. So by day two, we're talking about an example of we're trying to derive equations of motion for a pendulum. And it's not obvious right off the bat to students that you should try to use theta and theta dot as the state variables for a pendulum. It's not clear that you should do that. So what you can do, though, is say, let's use the exact same approach from yesterday. So I'll ask, what are the forces acting on the object? And they'll say gravity, no problem. And gravity should act on the center of mass. And then they have no problem saying that, yeah, the ceiling here or the pivot point, that's exerting some force on your pendulum. But it's hard to write down exactly how much. So I say, that's fine. Let's just leave it as undefined for right now. We'll just give it some symbols and we'll write down our equations in terms of that unknown force. And if you do that, then once you're willing to leave F as unknown, then it's no problem. They can write down these equations of motion, no problem. It's exactly like the example I did yesterday, for a reason. I didn't do that on accident. So once you've got these equations of motion, then I say, well, how can we quantify, like, what is this unknown force F doing? It's whatever force is required to keep the end of the pendulum fixed at its pivot point, which I think this time I put it 1, 1. So we know that this end of the pendulum is always going to be at position 1, 1. So we can write that down. We can express that end of the pendulum in terms of our state. And so we know that this quantity here is always going to be 1. And we know the second quantity, the y coordinate of that end of the pendulum, is always going to be 1. So at this point, now you've got a differential algebraic equation. This differential algebraic equation is a perfectly great description of the motion of a pendulum. It's not the classical one, but it is perfectly great. There's nothing wrong with it. You're good to go from here. If you want to convert it into the classical equations of motion, you can do that. There is a standard trick. These constraints hold at all times. So therefore, I can differentiate them twice if I want. And the resulting equations will also be true. They'll also hold at all times. So if I differentiate those constraints twice, trust me, you get this business. If you look at this carefully, you'll say to yourself, well, hey, I could take Rx double prime, shove it in here, right? That would give me an equation involving Fx. I could take Ry double prime, plug it in here. That would give me an equation involving Fy. I could solve for Fy and Fx. And if you look at it, I'll get an expression for Fy and Fx just in terms of theta and theta dot and theta double dot, right? Once I do that, oh, these are the expressions you'll get. They're not particularly nice, so I don't really, you can do it by hand. I did it, but I don't necessarily recommend doing so. So once you've got an expression for your forces in terms of theta and theta prime, now you can go ahead and plug those back into your differential equation on the last slide here for theta double prime, right? I theta double prime, this stuff involving my forces, and you simplify, and lo and behold, you get, this is the plane equation for a nonlinear pendulum. You get the correct thing. This is a little bit different than the thing you might have seen before, because I'm using a solid rod for my pendulum instead of a point mass at the end of a massless rod. And my pendulum has some width to it. But yeah, I mean, it's the right thing for sure. So that's super interesting. This is not, like, obviously, this is not the most elegant approach to do things, but it's very easy to extend, and it's very easy for students to get a hold of, especially if we automate the last bit of the algebra. So for example, on the next, so that would take me probably one day of class. On day 3, we're going to derive equations of motion for a double pendulum. Now, students, in my opinion, if you're going with a classical derivation, there's like no way they're ever going to be able to do this. But if you do things using the DAE approach, actually, it's quite doable. We start by focusing just on the first pendulum. I say, hey, what forces are acting on the first pendulum? And they know the ceiling is keeping the first pendulum at its pivot. And they know the second pendulum is exerting some force, and they also don't know how much that is. So we're just going to leave that undefined also. And then you've got gravity. And so they write down the equations of motion. F equals ma, those are sitting right here. And then I do have to tell them that Euler's law, that should be a net torque, and you should just add up the torques, acting on the first pendulum. But if you do that, then with a little bit of prodding, they do struggle a little bit with the trigonometry here. They'll calculate the net torque, and you'll end up with this system of ODEs. These are the correct equations of motion for the first pendulum. And then the second pendulum, they realize that, okay, well, the first pendulum is exerting some force on the second, so we'll give that force a name, F3, and there's just gravity acting on it. So great, you can write down the equations of motion again. And this is all really, really follows very naturally from the single pendulum that we did before. And now all we really have to worry about is our constraints. So our constraints, again, let's see, we have our first pendulum is pinned at 1, 1. That's these two. And then the end of the first pendulum, which you can express like this, oops, this side of everything, right? That's the left-hand side of these equations. The end of the first pendulum has to match up with the top of the second pendulum. Those two have got to stay together at all times. So you end up with these constraints. Great. You also end up with the physical constraint. They have been through a physics 1 class at this point. They know that those two forces acting at the pivot here, force 2 and force 3, those two should be equal and opposite of each other. So force 2 should be negative of force 3. But they can write this down. And now we get to have a good talk. This is actually a really productive talk because there's no way you're going to handle the algebra here. Not me, for sure. Because you've got 6 differential equations of motion, right? You've got three configuration variables for each of your 2 pendula. So there's 6 equations of motion right there. You've got 2 equations keeping the top pendulum pinned. So you've got 2 equations there. You've got 2 equations keeping your pendula coupled together. you're going to do the standard trick of differentiating your constraints, differentiating your 4 constraints, that gives you 4 more equations. And you're going to differentiate them again, that's 4 more equations. And then you've got your force balance constraints, that's 2 equations. So you've got a total of 20 equations that you need to satisfy with your unknown functions. Great. You've got 20 equations. How many unknown functions do you have running around? Well, you've got your unknown forces, F1, F2, and F3. They all have 2 components, so there's 6 there. You've got, right, you've got your position, velocity, and acceleration of each of those 2 pendula. So you've got 12 functions there, and then you've got the orientation of each of the 2 pendula. So you've got 6 functions there. So you've got 24 unknown functions, or like 24 variables, I call it. So you've got 24 variables, you've got 20 equations. At this point, they have probably seen at least some linear algebra. They should realize that, yeah, 24 variables, 20 equations to satisfy. Hopefully, you can choose 4 free variables. How should you choose your 4 free variables? Well, you can choose them a lot of different ways. There's a little bit special about theta 1, theta 2, theta 1 prime, and theta 2 prime, but in principle, you could choose a lot of different free variables. But we talk about, okay, if I choose those 4 as free variables, I should be able to express all of my unknown functions in terms of theta 1, theta 2, theta 1 prime, and theta 2 prime, including theta 1 double prime and theta 2 double prime, which would give me just a nice system of 2 differential equations, one for theta 1 double prime and one for theta 2 double prime. And that should be the correct system of differential equations for a double pendulum. And it turns out that, yes, you can do that. It is no problem. You will have to cajole your CAS a little bit. The computer algebra systems don't particularly love doing this kind of thing. That's why we wrote software to do it. If you do the whole thing, I'm running a tad short on time. If you do the whole thing, here's your expression for forces in terms of theta, in terms of your thetas. Here's the expression you will get for theta 1 double prime and theta 2 double prime. It doesn't even fit on a slide. It's not even close. It's huge. You don't really want to do it. The point is that we do the same thing every time, and students love a systematic framework for doing things. So by the end of this 3rd day, they've gotten this far. So by day 4, I give them this problem, a coupled pendulum problem. So now I've got a spring connecting 2 pendula at different places. This is a reasonable problem for them to attack at this point. They write down the equations of motion for the first pendula, or first pendulum. It's no problem. You've got this unknown force F1, you've got this spring force F2 that you're going to have to worry about, and you've got gravity acting on it. Your constraint is that the first pendulum is fixed at some position. They can write down the same equations of motion for the second pendulum, and they're good enough to realize that F2 and F3, again, have to be equal and opposite of each other. The part where they're going to struggle a little bit is modeling the spring force, right? The spring force, well, you can kind of figure out the attachment point. It's a certain length down from the connection point. So that's this length right here. Let's see. It should point in this direction. Oh, no, these are equations for just your connection points. Once you've got connection points, you can figure out the distance between the connection points. Once you've got a distance between your connection points, then you can figure out the amount of extension or compression of your spring. That's no problem. That's right here. And then you know that the spring force should be directed in the direction from P1 to P2. So this is really, now the bulk of the work is here in modeling this spring force in vector form. It's the place where I want the focus to be. So if they do all that, if they can get those equations done, then they can use the software. Let's see, which one do I want? It's this one. They can express all of this in MATLAB. Can you guys, Kurt, can you see this? Do you need me to zoom in a little? I can't hear you, but you say good. Okay, great. All right. In MATLAB, they just define everything as symbolic things. They make R1 and R2 vectors. They make their forces vectors. You write a little helper to compute torque. They write down, here literally is the exact expression we wrote down for point 1, the attachment point 1 and attachment point 2. We wrote that down on paper. We wrote down that Q1, the pivot point for pendulum 1 has to be this. We wrote this down. We can write down moments of inertia. So they write these things down. They write down their equations of motion. And I'm running pretty short on time. Then they use this function we wrote called generate governing DEs. Generate governing DEs, it just does the trick of differentiate things the right number of time, solve for your forces, express everything in terms of the state variable you choose, and it spits out and says, boom, here are the governing equations that you want. These are them. This is correct. These really are the governing equations for a coupled pendulum. Undergraduate students, they can and have gotten right here. These things, these PPEs, these are expressing anything else you might want to know in terms of your state variables. Once they do that, then I can show them how to substitute in actual values for your parameters. They substitute in actual values for your parameters, and now they get definite DEs that they can deal with. Once you have definite DEs, you're not going to analytically solve these things. But what you can do is use a numerical solver and just time step it. Just use an Euler method. Just use something like that. Time step it, and you can see the energy getting exchanged between these two pendula. You can write down, since you have a numerical solution for theta and theta dot, you can write down equations for energy, and you can see energy being conserved. Or you can make a fun little animation and watch it go back and forth just like it does on the YouTube video. So the point is that if we're just willing to go to a DAE framework and we're willing to use some software to help with the terrible bits of algebra and differentiation, then we really can get students to do interesting mechanical problems that hopefully kind of piques their interests and keeps them thinking that math is a thing they should pursue. Thanks for listening. If you're interested, you can always email me at this email address. You can find the code that does this, the code for generating the governing DEs at this GitHub place. And that's it.
Thank you so much for your presentation. I'm going to